Hello and welcome back to sections 17.2 through 17.3 as well as 17.5. In this video we'll be using example 1 here to analyze the curvilinear translation of bar BD. So if you visualize G here, so G is going to just kind of move in some kind of an arc, so it won't be a straight line, so it's curvilinear motion. But it's not general plane motion because as we say get up to here, our bar will still be oriented in the same manner, so it won't have any rotation there. So it'll be translation only, but it'll be curvilinear translation. So we have our general free body diagram over here. I've gone ahead and sliced through these two members. We can treat them as two force members. And then I have my center of gravity over here. So a lot of times what we're doing is we're saying sum of forces equals mass acceleration. So we have our forces and moments over here, and then we have our accelerations on the right. And that will just follow that form of the sum of forces or the sum of moments equal to mass acceleration. So kind of our general equations of motion type thing. And again, this also applies for just sum of moments equal to I alpha. And then plus some stuff if we choose a point that's not the center of gravity or a fixed point. So our accelerations. So in this problem, we've already shown that it is a curvilinear problem, so we should probably use a normal tangential coordinate system because of that. So tangential motion at this instant will be to the right because of this omega is going to cause this bar to rotate, which is going to cause this whole thing. So I only really care about analyzing this yellow bar down here. So we have tangential here, and I will have AG tangential to the right. We expect as this moves right, this will also move up. So I'm going to, my inward, so the radius, so the curvature points inward. So we'll have our normal direction pointed up here. We'll have AG normal. And then, as we established, as this bar kind of goes about, it doesn't actually change its orientation. It just changes its position. So it doesn't rotate. So we don't have this case where it's like rotating and translating at the same time. It's just swinging. So it always remains flat. So in that case, we can state that alpha is 0. Omega is also 0 in this case. But we only care about accelerations over here. So alpha is 0, and I'll just draw that with right-hand rule. And so now, to analyze these, we're going to look just at the yellow bar, and we get to use 3 equations because it's a planar rigid body. So we have sum of forces in the normal, sum of forces in the tangential, and then we also have sum of moments, and we can do that about an instantaneous center, or about G, or about any other point that we choose. So I could do moments about G. If I do that, I'm going to have 2 unknowns, because these are both going to produce a moment about G. So instead, we're going to choose that case where we choose an arbitrary point P. So I can do this about B or about point D over here. And what will happen by choosing one of those points is I will eliminate one of my unknowns from the equation. So I'm going to do this about B, but you could just as easily do this about point D. So sum of moments about point B, I will assume right-hand rule positive. So this is going to be equal to, so because I didn't choose center of gravity or a fixed point, because B is going to move, it has a velocity, then I'm going to get IG alpha plus mass times AG tangential delta normal plus mass AG normal delta tangential. So this is not a statics problem. It's not sum of moments equals 0. So it's equal to all of these kinetic moments, which is why we set the problem up like this. So all of our moments will come from over here. All of our kinetics will come from over here. And then there's some dimensions that will kind of be shared. So if we look at our moments, we're going to look over here. Again, we're looking at just the yellow bar. So the 100 newtons acts at B, so does tension BA, so I don't really care about those. So I have this force G acting downward. it acts 1 meter away, and it will produce a negative moment as I've defined it. So determine your senses manually. These are 2D problems. If you don't want to do that, then you have to use vectors. So still doing moments, going over here, we now have tension DC. So plus tension DC. This acts 2 meters away from B. It will produce a positive moment. So that is for our moments. Now we go and we fill in this piece here, IG alpha. So IG alpha, so this is a slender rod. So I will need to look up the, well, actually I don't, because we established that alpha is 0, so therefore we don't care about what IG is. But if alpha was not 0, I'd have to go look up the equation for a slender rod. So we get a 0. Mass, acceleration, delta n. So our tangential acceleration is going to be to the right, which means that it will be in line. The line of action will go through B. So we're going to get another 0. And then we have our last term. So our acceleration in the normal direction, in this case, will be upward. So we drew it upward. So that will have, so mass, so the mass of the bar is 50. The acceleration of gravity normal, so we will figure that out. Actually, I think we're going to sub out for this. So yeah, we're going to sub in that omega squared times r term here. All right, so just a bit of a, so omega squared times r is fine, but it's not between b and g. It's actually g up to this point up here. So let's rewrite this in a way that probably makes a bit more sense. So instead, so we still have our initial equation, sum of moments equals IG alpha m, and then so this is all fine. And I've rewritten everything down here except for when we sub out the acceleration to normal. So let's write it in the way that we're used to. V squared over rho. And so again, we're looking at just the yellow bar here. And so this is going to have some velocity to the right because of it's going to be the same. So the velocity to the right at B is the same as the velocity to the right here. And that's going to be caused by this bar. So we can find that pretty easy. That is just going to be this 1.5 meters times this 5. And that'll cause it to be to the right. So FG -1 plus t. So just rewriting this, so I'm going to skip these zeros. This is 490.5. So 50. So our velocity we can write as 1.5 times 5. And we're going to square that quantity. And then the radius, so rho, again, is for finding all of this. So it's also this 1.5. Because we're basically trying to find the acceleration. So the acceleration to the right at G will be the same as the acceleration to the right at B, because the bar does not rotate. And then our delta t. So how far in the tangential direction are we? So that is our 1 meter here. So again, we're looking at our acceleration upward here at G based on B. So we move up here. So we're 1 meter away, and we go around this way. So we have a 1, and then our sense is positive 1. So we put everything, we put all the numbers in as positive, and then we determine our sense manually as positive 1. And so now we can solve this for tension DC, and it will come out to be 1,182. 1,180, well, 3 if we round. 82.75, which, if we keep 4 sig figs, is 1183 newtons. All right, so that's one of them. To find the other one, we could do another moment equation. So we could do a moment about G, and we could do all of that. But it's much easier if given the option to just do a sum of forces. So let's just do our sum of forces in the y, and the only things that will show up will be the tension, the weight, and the other tension. So I know the weight, I now know this tension, so I'll find this tension out of that. So sum of forces in the in this case, it's not y, it's the normal direction, but it is upward. And that is going to be equal to the mass times acceleration of gravity in the normal direction. And so again, we did this thing, mass acceleration normal up here. So let's do our forces first. So our forces all come from this diagram. So we'll have tension BA, negative weight, tension DC. So let's do those first. So we have tension BA going up minus force due to gravity plus tension DC. Again, I know this and this. This will be equal to the mass. And then for acceleration of gravity, so we could sub in the omega squared r, but it's probably more understandable if we do v squared over rho for this one, where we're trying to find the acceleration due to the rotation of a different bar. So let's plug in what we know. We do not know tension BA. We know that this is 490.5. We know that this is 1183. We know the mass is 50. We already did this. It was 1.5 times 5 squared over 1.5. Oops, you can't see any of that. There you go. So v squared over rho, same stuff. The only thing we don't know now is tension BA. We solve for it. You will find that it is 1,183 as well. So same numbers, they're actually balanced in this case, which would make sense. Alright, so again, just kind of recapping, we had a bar. This bar was going on curvilinear translation, so it was swinging, but the orientation wasn't changing. So we broke the bar apart, we cut through these two force members, and we found tension BA and tension DC. So we started by finding tension DC by doing some moments at B, so that this wouldn't show up. We established that we didn't have any angular acceleration because the bar wasn't rotating. We established that our tangential acceleration was going to go through B, the line of action would. And then we were only left with this on the right-hand side. To find that acceleration normal, I elected to use v squared over rho because I was looking at a different bar. You could have done the same thing with omega squared r, but remember that your r is this r and not this r. Once we found that, we came back to sum of forces in the normal direction because we only had one unknown left, and we solved for that. All right, if you have any questions, feel free to contact me.